is a definition of a sample space. Now, a sample space is just all possible outcomes of an experiment. And an experiment is a controlled operation that leads a set of results. For example, tossing a coin, rolling a die, rolling 2 die, etc. It could be any number of things. It could be going out and recording some information from individuals and finding out what year they were born, how tall they are, what their eye color is. There's any number of ways to do it, but we want to talk about it in this kind of theoretical way at first, which is an experiment is something that we do. And the best way to kind of illustrate that oftentimes is with things like dice and a coin toss. And a sample space, as I said, is just an outcome of all possible things that can happen in an experiment. So the first thing we want to look at is the top one, the yellow part in this little image right there. The top part is the sample space for the coin flip. There's only 2 of them. There's the head and then there's the tail. All right. So the outcome or sample space for the toss of a die is 6 different possible values. Well, if there is a midterm, then it'll be the department. Haven't heard anything, so maybe they won't give us one. So that'll be good. You just have to take that test too, which will be on chapters 4 and 5. The reason why I've got it in there is just because with the normal online courses, the ones that they do, they call them asynchronous. It's basically the ones that they've had for years. They kind of force our hands and make each one of those to have a midterm and a final, and they got all these crazy rules about how much they're going to count. And so I just wanted to put that in there as just to kind of hedge my bets in case they came along and did that with this course. I'm kind of, as we're getting closer, I'm kind of thinking they're not, though. So that'll be good. All right. Now, an event is just a sub-collection of the outcomes of an experiment. So for example, if we're talking about the rolling of a die, we could say an event like odd number or even number, or numbers greater than 3, or just a single number like 5 or 3. And so with those definitions, we can build basic probability. Now, let's talk, and basic probability, we'll see the definition in a minute, but let's look at the basic probability rules. I'll tell you what. Let's just go through the rules first. I was going to say let's talk about the formula first, but it really doesn't matter that much. Okay, the probability of an event cannot occur, something that's impossible to happen, is 0. So in other words, if somebody tells you there's 0 chance you're going to get out of this world alive, that means that it's not going to happen. And the probability of an event that will occur is 1. Now that gives us a picture of the extremes of possible probabilities. So we can have impossible or 0 on one end and certain or 1 on the other end, and everything in between is game. Now, what that essentially means is that the probabilities will always be fractional. Now, when I say fractional, that doesn't mean they have to be written as a fraction. They usually can be written as a fraction, but sometimes you could write them as a decimal. It just depends on the context, what's asked for. But because of the way that the probability formula is structured, and I had to write it like this because I haven't had really time to put it into a form and make it look nice and neat like some of the other things that I do. If I had the time, I could do it right now while I'm talking to you, but it takes a little bit of time to do it, and I have to use this thing called latex, and you have to use sort of like programming to get it to look nice and neat on the screen. But the probability of an event A, and A can be anything, like the probability of odd numbers rolled on a dice, or the probability of a head, or the probability of even numbers on a die. And like I said, it's really endless. Those are just the kind of the simple examples. Well, the probability of an event is simply, for the denominator, you have the count of all possible outcomes. And in the numerator is the count of outcomes in that event. Now, because of the way this works is you will always have a larger number on the in the denominator than you will in the numerator. Therefore, that's why it's always fractional. It can be 0 or it can be 1, but it forces this to always be in between 0 and 1, or a fractional value. And this works for both theoretical and empirical. And I say this because sometimes there are books that, how would I say this? They belabor the fact, and they like to give formulas so much that they give formulas for both theoretical and theoretical and empirical, or what they call experiential probability, and they're really the same thing. Like I said, that's just one of the things that kind of annoys me about the way some books handle things. Hold on a second. So so that's why I just have one formula there, and I generally try to do that for most things, because I don't want math to be about, especially this course, to be about remembering things. All right. So that's the formula for basic probability that you will always use, no matter what kind of probability it is. And as I said before, since the denominator is always larger, a probability is always going to be fraction or decimal between 0 and 1 inclusive. It's not possible to have something greater than 1. It's not possible to have something negative. All right. Now, we got some examples here. Hold on a second. I'm going to write. All right. So let's look at this first one. Find the probability of rolling a 6 on a single roll of a 6-sided die. All right, so let's go over to the board. Let's see what I'm going to copy that. And paste it. That'll take less time there. Plus, it just looks better. All right. So now what we're going to do is we're going to write the probability of, and you can replace A with something that's meaningful, but A is just kind of like the, general way to do it. So I'm going to put a 6 there. You can put on a die, whatever you need to, but we got that die up there. Now, in the denominator, and I'm going to write the little fraction here and put another one there. And then we're going to do it kind of step by step. Number on outcomes. Probably should have Number of outcomes on the die. Number of sixes. All right, now hopefully this is pretty self-explanatory. As we saw on that little example of a sample space, the visual, there are 6 possible outcomes on that die. You got 1, 2, 3, 4, 5, and 6 on there. And how many of those are 6s? Well, there's only one of them. So therefore, we've got the probability of rolling a 6 right there. It's just 1 6. Now, if you were asked to round that off, you would have to be told to what space. Now, what decimal place. And this is why you got to be careful with statistics because of rounding errors. Now, some values are going to be perfectly, if you have something like 1/4, that can obviously be written as 0.25, or 1/2 can be written as 0.5. But something like 1/6, if you were to take it and put it in the calculator and do that, take 1 divided by 6, it's going to fill up your screen because it's what's called a repeating decimal. So there is no way to have an exact value. So you have to be told to round off. So pay attention to what you're told to round off if you're asked to. All right. There's another one. All right, so let's go over and just look at the sample space. I've got a little visual in here. There it is. We'll move it up here. So here's our sample space for a 52 deck of cards. And the reason why I put this up here is because there's usually somebody that doesn't know about cards. They don't never played them. And so we need to look at it and just verify. But this is 52 card decks, or sometimes the the artwork might look a little bit different. For the most part, you'll have 4 suits, they're called, and that's what each line represents: the diamonds, the clubs, the hearts, and the spades. And each one of those suits has 13 cards. All right. Now, just a couple more words. For each one, there's 10 numbered cards, and I'm also including the ace on that, and that's not that big of a deal. Some people include the ace as something different, but there's also 3 face cards, and they call face cards because they got a picture on them. All the rest of them are just basically numbers, and then the number of dots that represent that. So why does an ace have only 1 dot in it? Well, it's sort of 1, but can be also be used as a kind of a wild card in a sense. It has a lot more power. And in some ways, it's kind of like a king in chess. It's got the lowest value in one sense, but it's also powerful because in blackjack, and poker, it can have more value. But I don't want to get into all those rules. But anyway, let's go back to our example and answer this question. Now, so we want to select a diamond. Now, as we hopefully saw over there, there are 52 cards. That's why they call it a 52 card deck. You can just say no number of total cards, just to kind of be specific. The bottom is always the total that you're pulling from. And up here is the number of diamond cards. All right. So does anybody remember how many cards there were in there? Well, there's 52. The hen is up there in the line, a 52 card deck. Now, from that picture, we're talking about diamonds. The whole first row is diamonds, and if you count them, there's 13. So 9, 10, 11, 12, 13. So I'm sorry, 10, 11, 12, 13. So there's 10 with the numbered cards and then 3 face cards, so that's 13. So let's go back over there. I put that in. All right, now, generally speaking, if you were asked to put it in as a decimal, you would have to probably round it off. You may have to round it off. In this case, though, this is perfectly suited because 13 is a factor of the denominator, and 13 goes into itself 1 time and into the denominator 4 times. And this is also what I had said a few times. Probability and proportion and relative frequency are the same thing. The proportion of cards in that deck for diamonds is 1/4 of them are diamonds, right? So these things are all 3 the same thing: relative frequency, proportion, and probability. Look at that last one for basic. So find the probability of selecting a black card. All right. So I'm just going to say down at the bottom, total. It's always the number. That's why at the end of this chapter, we go over something called counting methods, because with these examples that we're looking at here, it's easy to look and count. But oftentimes with big things, you have to use counting methods, and you don't need to know what they are so much as just how many. All right, so still 52 cards. Now the number of black, well, let's go back over and see. If you'll notice that there's one set of blacks cards that are called the clubs and one set of black cards that's called the spades. So that means then there's 13 plus 13, so it's 26. And again, you could see that, hopefully see that this 26 will go into itself once and into 52 twice. So this is 1/2. So essentially what that means is that 1/2 of the deck has black cards in it and 1/2 has reds. All right, any questions? I know it seems like I'm running a little bit fast, and so you can slow me down a bit. I just last night, was my when I first go over something, I kind of get a little bit of an idea of what pace I need to go. And last night I probably started off too slow, and then kind of had to speed up towards the end. So don't feel bad about asking questions. did good on the test. I didn't realize until yesterday that I had to actually post the grades, but somehow on the multiple attempts, you did get to see what your first one was, because some people told me that, but evidently after the fact, maybe it's because there's more than one attempt. I have to actually physically post them, and I was happy to see there were a couple of hundreds in there and a nice scattering. Maybe when we get to chapter 6, I can kind of show you a little bit of graph of that to see how it represents a normal distribution. All right, so let's go back. All right, now as I had said up here, there's two kinds of probability, and sometimes books kind of cloud the issue because they try to treat these differently and they'll give you a different formula. But really, the probability formula is always the same, with the total number of possible happenings is in the denominator, and the number of outcomes or number of observations in what you're looking for in the data to find the probability of goes in the numerator, which ensures you're always going to have a fractional amount. Now, this is just an example of empirical probability, and oftentimes it's taken from something that has to be collected. In other words, you have to perform experiments, and sometimes this is with certain books, and certain teachers will call it experimental probability. All right, but it still works the same way. Is if you and for example, in this example, they went out and they collected data on a certain number of people in the U.S. and found out what their gender was, male or female, and then with each one of those, they found out what their education level was, and they grouped it into 6 different ones. Not a high school graduate, some college, but no degree, associate's degree, bachelor's degree, and advanced degree. All right, so hold on a second. I'm trying to get over to get some information out of the PowerPoint so I can make this a little bit quicker. Now, in order to find out what the probability of selecting one from this, and these are in millions actually, but it doesn't matter as long as we just know that that's what it represents. So here's what I'm going to do is I'm going to add up the total number of men. All right. So what we're doing is we're just adding up that row, okay? Now, that's going to be helpful for us because we're going to need that for our numerator. But what we also need is a total of all of them. Now, rather than kind of reinvent the wheel and go back and add up all of them, since we know what the total number of men is, we just need to go out and go and do the total number of women. And then add those two. All right, so the total number of women is 101. So total of both or all the data is 94.0 plus 101.0. And what does that equal? So what that means is this was a survey of 195 million folks. But we're just going to write it as 195 since we're taking off what that means is we're taking off a bunch of zeros. So we're just going to do that for both of them so the proportion will stay the same. So probability of a man or male, that's what it is. All right, so I'm gonna go over here and write this over on the other side, and like I said, it'll look a bit nicer on the board. It's really hard to do fractions like this, with text, so I have to write it. Number of males and then the number total. So as I said, it was 94.0 over 195.0. And then if you whittle those numbers down, you get and the instructions on that, if you didn't see them, it said round to 4 decimal places up at the top. All right. Let me show you. That's important. I want you to be able to make sure you realize that you do need to make note of when it's asked to round that you do that. All right. See up at the top, 4 decimal places. Because this one is not going to come out even no matter what you do it. And then usually for empirical data, that's what they ask you to do. So back on the board. So 0.4826. If I take 194 and divide it by 195, that's what I get. And you see that's about 0.48 number or proportion. It's not quite 0.5, but it's getting pretty close. So generally speaking, you would kind of expect that about half of people in the US and half would be male and half female. But it's pretty close, and I'll show you a little bit of something in a minute. So there was another one I wanted to do. The other one was find the probability that one chosen at random is a male with a bachelor's degree. So this is, that one should have been 1. All right. Now, we're still dealing with the same total values. We're just kind of, and that's a with sign. So it's still going to deal with the total at the bottom. And up here, though, it's just going to have the difference going to be number men or male with bachelors. If you want to see this in a little bit more better light, you can go. This is actually one of the problems that I've taken from the book and the PowerPoints. I've just kind of broken it up a little bit differently. So we're still dealing with the 195 down here. And then I'm going to go back over and show you on the data where we get that numerator. All right, so back to this. Now, we want something more specific than just the male, so we don't really need to add anything up. What we're doing is we're going to the crossroads, and I can't really highlight it, but I got my cursor running around that circle over the number that represents male bachelor's degrees. And then this is the female, but we just want the male. So we want 17.5. And now we're simply going to take this. And I should have put a little squiggle here, because what that little squiggle equal means, it means approximately. And you just have to remember, if you have to round something off, then it's to a decimal, it's no longer accurate, and that's why that's used, if it's rounded it off. So let me put that in here and see what that number is. Actually, on the PowerPoint, I noticed that it was wrong. So like I said, that's supposed to be a squiggle. Oh, and I forgot to put my camera on. Give y'all two just to, so it's 0.0897, 4 decimal places. All right. Oh, I know what's wrong. I was trying to do that camera, and there we go. All right, so because this is that older computer, the big one that I do the writing on, it's got it's old. It's got the camera is hard to see, but I got a separate one, and it's got to be changed. Okay, so let's go back. Make sure I don't have any questions, and let's just finish out the basics of probability. By just talking about the difference about experimental or empirical probability and theoretical. Now, theoretical, just by its very nature, tells us that the probability of rolling a 3, sort of similar to what we talked about when we talked about rolling the 6, is 1/6, because there's only 1 3 on the whole cube, and there's 6 sides to that cube, so 1/6. is, as I said, that's the exact value is 1/6, and you have to round it off if you take it to a decimal, because if you were to take it and put it in your calculator, it fills up the screen, and that's why they put that little line over that 6, just meaning it repeats on and on. But just as just an example, to go back up to the first thing where it says experimentally, how do we, let's say we rolled a die 12 times and got the following results. We got 2 4s, we got 1 6, we got 2 1s, we got 2 2s, we got 3 3s, and we got 2 5s. Now, if at, it had been true to experimental, if the experimental way had been true to theoretical, that means that we would have had exactly 2 3s over the 12, and that would be the same thing simplified down to 1 6. But let's just see how this works, because there's something called the law of large numbers. All right, and you might think that there's a conflict there, but there's not. So I've got a little experiment here, and you can do it. We're going to try to do it with this coin flipper that I got online. But we're asked to flip a coin 10 times and record the number of heads as a ratio over total flips, and then do it 25 times. Well, I got a couple of coin flippers here. Let me put that up here. So you can see it, and I'm going to go through and do that. This thing makes it real easy. It takes a lot of time if you do it with a real coin. All right, so this little thing, it's got ads in it, and you can pay for it and get it free, but I'm not going to do that. All right, so what I'm going to do is I'm going to say flip a coin 10 times. All right, and then they're going to show us the results. All right, now you can keep track of these. On that, they tell us what the results are. So there's 6 heads and 4 tails. Notice that they're not half and half. We know that that's the theoretical probability, but actually on the experiment, 6 of them are heads. So that's 6 over 10 or 0.6. Well, let's go and we'll do the next time. We said we wanted to do, what was it? 25 times. Now, 25 times, as you might notice, there's no way to have exactly half, but it doesn't matter. So let's do 25. All right. So on the flip 25 times, we've got exactly 16 heads over 25. All right. Still not, what would that be as a decimal? 0.64. It's even a little bit higher. There's a few more heads than there were in the last one proportionally. All right. Then we'll do 50. I think is what I said next. Yeah. And then they tell us there were exactly 25 and 25. What about that? 25 heads out of 50. That one is right on. All right. Let's do it a couple more times. We're going to do one for 75. And they tell us that there are 43 out of the 75, which is 0.57. So it's less than 0.6 now. It's getting closer to 0.5, which we would expect it to be. And let's do it one more time. So for 100 times, we've got 46 heads out of 100. Now, that's lower. In other words, that's 0.46. Now, what I'm going to do is add up all of the heads we had. We had 6, 16, we had 25, we had 43, and we had 46. So we had 136, and the total number of flips was 100. Let's see, 200. Was 260. So when we take 136 and divide it by 260, we get 0.52. Now, notice how it moved from being high, 0.6, down to 0.47, and then it got a little bit closer. There's another little thing that can kind of show you how this works. Let's see. Where's it at? A little visual. So this is kind of the same thing. This is actually in the book as well. So I'm going to put it in that note so you can see it. Whoops. So this is just an example of someone's experiment of doing it over and over. And you could do these experiments over and over and still not get the same thing as somebody else. But just like the M&M experiment, as we collect more and more of them, we're going to gradually get closer and closer to our proportions that we would expect. So this is something where they did, they show the number of flips. The red line is representing perfectly 0.5, half heads, half. And you'll notice that it bounces all over the place. So as you go along this x-axis, the number of picks gets higher and flips gets higher and higher, and it gets closer and closer to half and half over those many trials. So in a way, you could say this is how the theoretical probability is determined, by doing something many, many, many times. So all experimental probability or empirical probability will lead to a theoretical result. And they're both calculated the exactly same. One just comes from trials or experiments, and the other ones are obtained from something that we already know and are sure about. And there's a little video in there if this is kind of somehow puzzling you and you want to watch it. I'm just not going to take up the class time to watch it, but it's right here. It's a neat little thing. All right, any questions before we move to the next? Okay. All right, now when you hit basic probability From there, you still are going to use basic probability in a couple of situations. And those situations, there's a few rules. All right. Now, there's what we call compound probabilities, and that involves what's in sections 4.2 and 4.3. 4.2 is called OR probability, or the addition rule. So that simply means that when you have compound events, then it means add the basic probabilities that you have to establish, and then that'll tell you what the probability of OR is. Now, when we're talking about the probability of OR, this means specifically that if we do one experiment, we want to find the probability of getting this or that happen. Not just one thing, but this or that. Now, just common sense hopefully will tell you that if you do two things and you put two things into the mix, that your probability is going to go up. And so that's why this OR means add, because you're going to start out with two probabilities that are less than one, two fractional amounts, and you add them and you're going to have a larger fraction. Now, but in order to do this, we got to get two things straight. We got to talk about when items are mutually exclusive and when they're not mutually exclusive. Now, these two things here are called a Venn diagram, and those who use it 120 probably remember a little bit about this, even if you don't remember the exact situation. But a Venn diagram is just a way to visually show the relationship between two sets. All right. Now, on the left is what we call mutually exclusive items or events. That means things that cannot occur at the same time. All right. So examples of mutually exclusive events are, let's say A is the odd numbers and B are even numbers on a die. Those two things, they fit together. There's three of them each. And so there's no overlap. They're kind of interlacing. There's no overlap. There's three odds, three evens. You put them together and you got all the numbers in the die. But there's no overlap. So they're considered mutually exclusive. Now, for situations like this, when you find the probabilities of two things that have no overlap, what you do is you just take the probability of the first event, the probability of the second event, and add them up. All right. Now, on the right-hand side, if you've got things that overlap, essentially what you got to do, and this is what this little part is on the far right, it says the probability of A plus probability of B. That part is the same, but we have to subtract out the probability of having anything that's in both events. Oh, and just to kind of finish out, another example of a mutually exclusive event is A is a diamond suit in a 52 card deck, and B is clubs. There's no overlap. But non-mutually exclusive events are A is equal, if you have an ace and B is a red card. Notice that these things overlap because there are red cards in that deck that are also aces. So the reason why we have to subtract out the probabilities is because if we don't, we could end up counting things twice. So we have to subtract out the overlap. And then another one, for example, is A is a number on a die. Hold on a second. Less than 5. So a number on a die less than 5 would be 1, 2, 3, and 4. And B, an even number. Well, you've got an overlap because even though 2 and 4 are less than 5, they're also even. All right. So let's look at some examples of the OR rule. We'll look at a couple for mutually exclusive. And that's what that means. It just means mutually exclusive. And then not mutually exclusive. So when you got mutually exclusive, then simply you just got to find the two probabilities and add them up. All right, find the probability of selecting one card from a deck, and it is a red card or a club. Let's go back over to the board. So as I said, these would be mutually exclusive events. All right. Well, I'm thinking, let's see who else showed up. Elizabeth, the other. I don't see anybody else. Oh, wait. Oh, take it again later. All right. So the probability of red. Now here's our key word is or. I'm just going to write it out, the whole thing, where we're going to do it. This is the formula. Now, the one thing that's good about that formula is not, and like I said, is I kind of sometimes think we could simplify things by just saying there's really one formula for or, and it's the more complicated, the one that was on the right. And if we kind of state it like that, then we can say that if there's no overlap, then that part of the formula is going to be 0. So that's why it happens. So that's it is. You can just kind of remember, remember that one formula, and then realize that if you got mutually exclusive events, then this minus thing is going to be 0 because there's no overlap. So then this is going to be the probability of red. There's exactly 26 reds over 52. And then here, the clubs, there's 13, or, that's the one before 1/4. Now, I'm not going to simplify them until I add them up, and because if you do that, it's kind of counterproductive. Then you got to go backwards to find your denominator. So this is going to be 39 over 52, which, if you take 13 into both, you get 3 over 4. Okay? Questions about that? All right, let's go back to the die. All right. And these are the easiest ones to do. And I mean, I kind of struggle with it, and I think books too as well, because it's kind of easy to go back to what we call theoretical things, and usually the theoretical things are things like this, like the die and the cards and coins and things like that, because those are pretty well established. Because you can use anything, and if you look at that law of large numbers video, they even mention about insurance rates, that's how mature insurance rates are set, by using the law of large numbers and finding probabilities that way. So you can do that, but it's kind of I think a little bit wise to stick with the things that we kind of know what the probabilities are in order to make the principles simpler. All right, so a 4 or hold on. Yeah, this is right. All right. So the probability, we need the probability of the 4, and we're going to add to it the probability of the odd. And just so you realize, these are mutually exclusive because 4 is an even number, so there's no overlap. So just like with the 6 and the 3, there's exactly 1 4 out of the total. And we talked about a little bit about the probability of odd in one of the examples of an event. But there's exactly 3 odd numbers over a total. So then we add these up and we get 4/6. And then we can whittle this down to 2/3. Okay? Let me know if you got any questions. We'll take a break in a few minutes after I finish this, the OR thing. Okay, any questions? All right. All right, see, what did I have over there for an example? All right, find the probability of selecting a card from a 52 card deck and getting one that is red or a face card. Now, we have to kind of remember back to our sample space that these two things are not mutually exclusive, because you can have a red card that is also a face card, because looking at the sample space, if you look at just the first diamond suit, which is a red suit, and then the red also means the second one, then in the first one, you've got 3 cards that are face cards, the jack, the king, queen, and the king, that are diamonds. You also have 3 that are hearts. Total together, that's 6 red cards that are also face cards. Now, if we do not recognize that, then we essentially end up counting them twice, and our probability is not going to be accurate. And sometimes you're not going to notice it. Sometimes you'll do this and you'll come up with a probability more than 1, and maybe that'll be a little hint, but it's not always going to happen. All right. All right, so let's go ahead. We wrote it over there, so we want to go back to the board, right? So now, red or face, we'll just say. All right. So we're just going to simply follow the formula that we're going to find the probability of the red, the probability of the face, add those up. Now, here's where we got to recognize what to do. As I had said, is both mutually exclusive and non-mutually exclusive, you're always adding. It's just a question of whether, if you have this, is going to exist if they're not mutually exclusive. Otherwise, if they're mutually exclusive, then that follows the minus sign is going to be 0. Because there was no possibility of having something red and a club. There was no possibility of having a 4 or an odd number together on that one roll. But here, this is possible. So what I put is red and face. And I'll just put face so I can hopefully squeeze it in here. I don't think I'm going to have enough room, so I'll just put it below it. Okay, the probability of it was red. Remember, we looked at something very similar, which was the black, I believe. Exactly half of the deck is black, or 26 out of the 52. It really doesn't behoove us to put the 1/2 there, because then you'd have to go backwards. So I'm leave it as the unsimplified fraction until we get to the end. Now, there are how many face cards? There's 3 in each suit and 4 suits, so there's 12 face cards. Now, we have to realize that there are 6 of them that are red and face cards. So that ends up being 26 and 12, that's 38, minus 6 is 32 over 52. And like I said, is in this case, you could have still, if you hadn't noticed that there was overlap, you would notice that you had proceeded wrong, because 26 and 12 is 38. But in some cases, if you don't recognize that, you'll end up with things where you have a probability of over 1. So you sometimes will get the hint, but not always. And then we'll just write this down. So that's 8. Let's say 16 over 26, 8 over 13. Okay. All right, so this is the last one for the not mutually exclusive. All right, y'all got any questions? Y'all are asleep or what? Just playing like y'all are here, or I haven't heard anybody say anything. I haven't seen anybody even type anything in the last hour. All right, so last one for the not mutually exclusive. So so this is the probability of odd or, and I'll just put greater than 2. So again, it's always adding up the 2 individually. That happens no matter what for or. And then if they're the same, any that's overlap, we're going to do this. And like I said, is you can always put this in for all of them, and then just realize when they're mutually exclusive that that's 0. All right, so on that die, how many of them are odd? Well, there's 3 out of the total 6. Now, you may have to write this out. This is the event of greater than 2, and that's supposed to be a bracket, not a 3. I'm just 3. I'm sorry, greater than 2, so that would be 3, 4, 5, and 6. There's nothing on the die that's greater than 6, so there's only 4 of them now. There are 4 numbers on that die that are greater than 2. Now, how many, and like I said, we can also put them here, the other sample space, and put 1, 3, and 5, and then see which ones are alike. All right, so these are alike, and these are alike. All right. So all the other ones are unique. So there's 2 out of the 6 that are both odd and greater than 2. So this is 5, I see 7. So we come up with 5, 6. All right, okay. Well, it sounds like we need a break, but I'm going to do one more little thing because that'll finish up 4.2. All right, now, so this is the other thing in section 4.2. It's called the complement rule, and I think the one that they use is this one. And different books use different things. In Math 120, they used an apostrophe instead of the little superscript C. But all that just means is the probability of not being A. So if you have any event of A, hold on a second, this is backwards. So this is the way that they show the complement rule in the book, in this book. But all of these things are actually equivalent, okay? And the reason why they're equivalent is because this is one that just tells you what the complement is equal to. But all right, how does that sound now?
Yeah, I can hear you now.
Okay. I don't know what happened. I just swapped another jack on the USB jack. All right. So that's where the complement rule comes from. You can also look at oops. I got that wrong. You can also look at it the other way. If you know the probability of something happening, that you can simply find, if you know the probability of something not happening or the complement of that event A, you subtract from one and that gives you the other one. So this is really the main rule, because all probabilities have to add up to 1. You can go either way. So let's just look at an example of one using this part. And then when we get to the 5.1 a little bit, we'll see a little bit more about how this works. We'll get into it a little bit with some things. It's a lot easier to see it when you're talking about discrete probabilities. But anyway, according to Sky News, 35% of widgets sold in a recent year broke the first time they were used. What is the probability that a randomly chosen widget in that year did not break the first time it was used? So these two things are complements of one another. You've got the widgets that break, and then you've got the widgets that do not break. And those two things have to add up to probability of 1. It's sort of like with rain. If the probability of rain is 75%, then that means there's a 25% chance that it won't rain. And so 75 and 25 add up to one whole 100%. Well, we're just going to, we know that the probability of A is 0.35. And we know that this formula, that the probability of the complement is 1 minus the probability of A. Then all we got to do is just fill in this part to find the probability of the widget not breaking. So 1 minus 0.35, 35 is 0.65. All right, so let's take a little break. Try to come back about 12:30 or so, maybe a little bit later. I need to kind of get my head straight, and then we'll at least finish up the next section of probability, 4.3, which that one's a little bit more complicated. All right, so let's start looking at section 4.3, and this is the probably the most complicated part, and it's really just complicated because of one little thing called conditional probability. But we'll talk about that first, and then we'll kind of handle it. Now, this is one of the slides from the book PowerPoints, but it's a good example. And this is one of the things that I like about the way this material is presented in the book, because of the fact that it just illustrates pretty well how conditional probability works. Now, if you look at the first couple of sentences of this little paragraph here under the title Conditional Probability, it says approximately 15% of adult men in the U.S. are more than 6 feet tall. So how does that relate to probability? Well, remember, percent is one way to talk about probability, but essentially that means as a decimal 0.15. So that means if we somehow have all these people in a pool, these men in a pool in the U.S., and we go and pull one out, we have about a 0.15 chance of pulling one out that's greater than 6 feet tall. All right. Now, here's where the conditional probability comes in, and this is what I said is a good illustration. Now, let's say instead of selecting from men in the U.S. in general, we restrict the pool to only those men who play professional basketball. Now, obviously, that's going to change the dynamic some. For one thing, you're no longer going to have probably 200 or close to 200 million men to pick from in the U.S. You're going to be restricting the denominator now to probably a number that's in the thousands, probably less than 10,000. because I don't know exactly, because I'm not up on how many exact teams there are, but because I just really started following basketball this last season when we got canceled out, actually. And let's just say that there's 20 people on each roster for the most part. And you have about 40 teams, I believe it is. So that comes out to about 600 people who are active in playing professional basketball. There are probably some that are still looking for jobs, and maybe they'll pick up positions. There's also other leagues that are probably not as prominent. But for the most part, if people are playing professional basketball, they're tall. As a matter of fact, I've probably known one or two people that played professional basketball and they were tall, but I've also known and worked with people and had friends with the people that played basketball in college who were also tall. All right. And so that doesn't mean that they couldn't play professional basketball. It just means that they didn't have the opportunity or they didn't want to. So they were still taller than the average guy. So what that condition does is restricts that pool now. Instead of talking about 200 million people, it restricts the pool to probably 10,000. So now the denominator is smaller of who we're picking from. Now, when we pull out, the numerator will still be smaller than the denominator. So therefore, we're not going to break our probability rules. But there's a formula for probability that will always work, and it's written down here at the bottom. And I'm just going to tell you how that's written. Now, the book shows it two different ways, but the classic way is the way that's highlighted there in red. But there's a key word called given, and the way that first part, that left-hand side, is say where you have the probability of B, and then you have the line, and then an A. That little line essentially is read as given. So that essentially means the probability of B, given that A has occurred. In other words, given that we're going to professional basketball players now and not the population in general, that's what that's doing. It means we're restricting our pool. Well, it's essentially like this. The probability of whatever is on the bottom is what's given. So we're talking about the probability of pulling a man out greater than tall, given that he plays professional basketball. Well, the probability of professional basketball players would be on the bottom. And then in the numerator, to ensure that it's a smaller number, is you're going to have the probability of both of those things, that they play professional basketball and they're greater than 6 feet. All right. So that number is obviously still going to be a fraction, because there's no way that it can be any less than the denominator. It can be the same and be 1. But I also know that not everybody that plays basketball professionally is taller than 6 feet. There have been some that are shorter. I'm not exactly sure offhand. I remember there was one guy who was real short, like 5'2". He used to play for the Hornets before they came to New Orleans. Muggsy Bogues. There was other players. I'm not sure if this is right. I thought Allen Iverson was shorter, and a few others, but they were extremely good basketball players, so they could still play the game professionally. They had other talents. All right. Now, just to bring this up, this book does not use it, but there's an alternative way to look at it that usually makes it easier to do when we're taking and pulling the information from data, and I'll show you that. So remember, the denominator is still always larger, so the probability is always going to be a fractional amount between 0 and 1. So now we use this previous data to calculate two things. You remember we looked at this data of, we looked up two things. We looked at the probability of men that played, of men in this sampling group, and we came out to, what was it? Let's see. We answered two things. We just go back and see it. So we found the two things. We found this one from that same data, which was the probability of being a male from that sample space. And then the other one was probability of being a male with a bachelor's degree. Now, that's important because those two things are setting us up for handling this conditional probability for the next question. Now, we want to answer this question. What is the probability that the person has a bachelor's degree given, and there's our key word for conditional probability, given that he is a man? All right. So what we have to do then is in the denominator, using that formula here, we got to put down there in the bottom the probability for given he is a man. All right. I'm sorry. The probability that he is a man goes in the denominator. So we already had that figured out. So that's that bottom one. Okay. So let's, I want to take a picture of this so I don't have to come back to it. All right. So I'm going to write over on the new screen. All right. Somehow it defaults to red. All right. So I'm just going to put BD for bachelor's degree, and then I put the line given is male. So then the way the formula works is down here we need the probability of male, and up here the probability of bachelor's and male. All right. So we already talked about that the probability of male was 94 over 195. Now this is going to end up making a complex fraction, but I'm doing this to show you a little lesson. Now the probability of the male with a bachelor's degree was 17 over 195. All right. Now we can kind of handle this two ways, because I want to show you how that other formula can enter into the mix and why. Now, we'd already simplified these out. So I want to show you. What did I put there? It was 0.48. Oops, it was a couple more things. 4821. And then up here was 0.0897. Now, before I figure out what that is, I'm going to kind of come over here. Oops. And start again. And I'm going to show you. You remember when you've got a fraction, that is simply means multiply by the reciprocal of the denominator. So so the denominator has to be flip-flopped.
Wait, why are you doing that again?
Because that's the way fractions work.
Oh, you're just adding them up, right? I mean,
No,
working
multiplying.
them out.
I'm dividing fractions. So what are the rules for dividing fractions?
Okay, you're dividing. Okay, I got you. Yeah, you do flip it.
Yeah, you multiply by the reciprocal. And I'm going to try to do this to show you kind of there's an easier way, but I'm just trying to show you why this happens, all right?
Okay.
Now, because of the fact that these denominators are the same, when you do the inversion, you end up with 17.5 over 94. All right? All right. Now, we already know that this was this. So just using that previous work. Hold on a second. When you actually bringing things from data, you don't really have to go through all this, but they show you this. And I'm just trying to show you that there's a shorter way. And now in the book, they don't show you how those things go away. That's the thing about it. And like I said, I'm trying to show you that. All right, so 17.5 divided by 94 comes out to, and again, we're going to have to round it off. I think we said 4 decimal places. So this one right here is actually going to come out to the exact same thing. So the good thing about following the formula directly, if you have the probabilities already handed to you, like we did, you can essentially just jump to this part right here and it works. But I wanted to show you this because of the fact that I had introduced an alternate formula that you can use where you just use the counts. So if we go back over to that, see, I'd said here, if you have access to the actual data and can count the number of values, then you can do this. And that's what that little n means. It just means the number in A and B and the number in A. Well, you don't have to go through all this and do that flipping and all that and save yourself some work. Because you may not always have those probabilities already calculated individually. So just look at one last little thing and then hopefully you see what I'm talking about. All right. So if we had gone back, let me just go back to that data. All right. Now, we had already determined that the number of men was 94 because that's the total when you add up all that first column. We did that on that other page. Well, actually, we did it in the sheet, and I showed you how it was working. So that's the 94. So remember, we're looking for bachelor's degree and male in the numerator, and then the denominator is the male, which is the 95. And then remember this number here. The 17.5 is like the intersection, the cross walk between men and bachelor's degree. So that's where the 75 comes in. So therefore, you could easily, with that alternate formula that I have, just kind of jump to this and you get to the same place. Like I said, is the book, they do this right here, if you want to go back and look at that example, and then they just jump to the final answer. And they don't show you in between how that's happening. But like I said, is even what I could just show you too is you didn't even have to go through all this where you made yourself a complex fraction. You're just simply taking the numerators of each one of these and putting them over one another. And so it works either way. Now, if you don't have the original data and if you just have probabilities that are handed to you, you can still do it like that via the formula. Well, hopefully that's not blowing your mind too much. Like I said, I just try to put in things to hopefully show why things happen if you get to something and they don't show you why. All right, let's go back and finish a little bit on this. All right. So now that brings us up to the multiplication rule. And in a way, the conditional probability is a subset of the conditional rule. And I'll show you in a minute how it is. But when we're talking about two things happening, we're talking about multiplying the number of possible outcomes. So let's just say that we flip the coin twice. Now, instead of just having head and tail, we essentially have 4 outcomes. We have those 2 outcomes times the 2 outcomes. There's 2 heads, there's a head and a tail, times the head and tail. That means there's 4 outcomes when we introduce 2 tails. And as a matter of fact, if you wanted to do 3 flips of the coin, it would be 8. It would keep doubling every time. All right. And so again, you can't really show the sample space with every kind of outcome, but for something simple like where there's just 2 outcomes, it's easy to show. So this is the sample space. You could either have 2 heads, you could have first a head, then a tail, you could have a tail, then a head, and then you could have 2 tails. So that's because of what we call multiplication. 2 outcomes times 2 outcomes. So therefore, what we end up doing when we talk about something like this, let's just go ahead and look at this. Find the probability of flipping a coin twice and getting a head and a tail. All right, you can kind of see it on the sample space, but let me just show you how the multiplication works. And then we'll come back and look at that. All right, so the probability of a head and a tail is equal to the probability of a head times, I'm going to put in a little X there just for a minute. I mean, you don't really need to do that, but I just want to show you that the and means multiply. Usually, if you just sit them next to one another, that's enough. All right. So if we just go back to the original basic probability and think about the heads, how many heads are on a coin? Well, there's 1 head and there's 2 sides. All right. And then multiply, because that's what it's called, the multiplication rule. Now, how many tails on there? Well, there's 2 of them. Both are probably the same. Then when we multiply, we get 1/4. 1 times 1 is 1, 2 times 2 is 4. Now, when we said head and a tail, we were implying that that's the head on the first one and head on the second. And if we said something like we didn't care about the order, then we can kind of handle it a little bit differently. But you can go back to the sample space and see that there's only one with that order, head and tail. And I'll even put that in here to make it a little bit more clear. All right. So questions about that? I mean, multiplication is really even easier than the addition rule because you don't have to worry about adding and all that. Which fractions and adding is usually harder than multiplying. But you just got to remember, when you multiply them, you multiply the numerators and then the denominators. Let's put them here first. All right. One little thing. There's something over here I want to show you. And now, I thought we had mentioned this, but I want to mention this because this occurs frequently when especially when you have talking about multiplication. Any event whose probability is less than 0.05 is considered to be unusual. This is going to be a theme that's mentioned throughout the course because 0.05 is kind of the it's 5%. But 5% is what the book and most books use to consider something to be an unusual event. And that's going to be important as we get into the second half of the course. So just remember that. And let's go over to look at an issue. One problem. I'm not going to write it on there. I'm just going to look at it on the PowerPoint. But we're going to look at a thing in a minute where conditional apply, but I wanted to show you one thing. All right, here we go. Now, just like the addition rule, it doesn't have to be just one probability. You can add, if you wanted to say 3 or more items, you could just keep adding. Same thing with multiplication or the and. If you want to have multiple things happen, then you just multiply multiple probabilities. But this gives us some census figures about 3 major cities, the 3 largest cities, it looks like New York City, Chicago, and Los Angeles. And they tell us that the under 18 age of folks in New York City is 23.5%. In Chicago, it's 26%. Oops, I'm sorry. 23.5% in New York City, 25.8% in Chicago, and 26% in Los Angeles. Now, if one person is selected from each city, what is the probability that all of them, in other words, New York City and Chicago and Los Angeles, and I'm adding the ands in there for emphasis, that all of them are under 18. And then they ask if this is an unusual event. Well, there are three events that are independent. In other words, one is not affected by the other. And we'll look at dependent events in just a second to close out. But the probability of New York and Chicago and Los Angeles is simply the probability of New York times the probability of Chicago times the probability of Los Angeles. And you have to put them into decimals to multiply them. And then when we multiply all those, we get this value of 0.0158. Now, this is what happens when we multiply fractions. If you take two fractions and multiply them, you're going to end up with a smaller fraction. All right. So that's what, because now we're talking about more than one thing happening. So the probability will go down, smaller probability when we multiply. With or, we're adding and we're getting a larger probability. But with multiplication, we're getting a smaller one. So now, in order for all these three things to happen, we get a value of 0.0158 or 1.58%. And they ask us, is this an unusual event? And since the unusual event cutoff is 0.05, then yes, this is an unusual event, okay? All right, so now when we're talking about independence and dependence is essentially it's conditional probability, but it's just that we can still use the multiplication rule with it. We're not pulling it from data. We're actually going to just multiply, but we got to make an adjustment if we've got dependent. And let me show you what I'm talking about. If you take a deck of cards and you're going to have somebody pick two cards, and you hand them the deck and have them pull one card out, and then they remember what it is, and then we put it back in, reshuffle. We've still got 252 cards in the deck, and therefore they're still pulling. The same probability is still going to be the same on the second pick. Now that's considered independent if you put it back in. But if we let that person keep that card, and then we go and have a second pick, the probability of the second pick is going to change. It's conditioned upon what happened in the first one. There's no longer 52 cards, there's 51. So the probability scenario changes. And that's what makes this conditional or dependent. All right. So let's go over and look. I got an example. All right. Oops, what happened? Gotta go to the notes, that's why. So I'm just going to demonstrate first. This one would be without replacement, and then we're going to replace just to show. The first one is what's considered a dependent event, or it's conditional. So draw two cards in succession without replacement, probability of getting two kings. All right. Now they got two fancy formulas in there, but like I said, it's really still just the multiplication rule. It just kind of muddies the water. King and king. So that's simply going to be the probability of a king times the probability supposed to be a dot for multiplication. All right. Now, remember back to the deck of cards. So there's 52 cards, and out of that deck, there's 4 kings. Now, if we want a second king, then we have to have gotten a king on the first pick. And also, there's no longer 52 cards in the deck because they say without replacement. There's now how many? Without replacement. In other words, there's 51 cards in that deck now. Now, if we need 2 kings, then there has to have been one already taken. So there's also not 4 kings, there's 3 kings. So then that's when we have conditional probability or not independent events. So then what we got is 4. Let's see. So I'm going to whittle this one down. This is 1/13. Because if you do that first, then it's going to make it easier on the... Because if you want the exact answer, then you're going to have to simplify. And you got to watch it if they want exact answer, if they want you to give an approximation. They got to tell you what to round it off to. And then that's 1/221. All right, so let me just show you the same thing with replacement. And like I said, this is going to change because this second pick was conditioned upon what happened in the first. Because it's not independent now because we didn't put that card back in. I'm just going to say probability of K and K is equal to the probability of K. Still the same thing. And I'm going to kind of show you the formulas that they use in the book can be a little bit confusing. And I'm going to kind of go over there and show you. So now, the first pick is still going to be the same. There's still 4 cards out of 52. Now, since we did not put those back in, and so there's really no condition that affects that second one, so now the second pick is still the same, but the multiplication still works the same way. So this ends up being 1/13 times 1/13, and I do believe that's what is that, 169? 169. So they work differently. So when you see, let me find this, these crazy formulas, and they freak you out, I'm just trying to tell you that it's essentially all this is saying. Let me broadcast it on the thing there. Because this, like I said, this kind of, to me, muddies the water because they give you these two different things. But for any two events, you're still multiplying, but all these are essentially saying here and here. It's just saying that if these are not independent events, then that first pick will affect the second one. So you're just essentially going back to the conditional probability of saying the probability of B given that A has happened. But the procedure is still the same. You're still multiplying. It's a little bit more complicated than the addition for adding and having that intersection, but it's the same kind of concept. It's a subgroup. So you're still doing the same thing. You're still multiplying. All right. So I've been saying being on a roll here, saying too much. So if you got questions, let me know. We got plenty of time. I got one more little thing. We're going to go back to the complement rule, and we can use it for something else. All right, so oh yeah. All right. Now, you'll see this mentioned in here, and this term called at least once. And the reason why we can use the complement rule here, it's because that at least once is kind of nebulous. And I'll just kind of write on the board what I'm trying to, a point I'm trying to get across. It's just, this is a kind of a special condition. So this is the complement rule again. It's just that it applies in this because at least and none are complements of one another. And the reason why it just helps us to be able to use the complement rule here is because of the fact that at least once is really kind of hard to calculate. It's a lot easier to calculate the probability of none because there's a lot of events involved at least one. All right. But we can calculate none and then subtract from one and get at least once. So let's look at that example, and that's what we'll finish up with today. All right. All right, so this is sort of like a factory, and items are inspected by for flaws by that camera. All right. So if a flaw is present, each inspector will detect it with a probability of 0.8, or about 80% of the time, an inspector is going to catch it. Now, there are 3 inspectors, and they work independently. In other words, that 0.8 applies to each one of them. One does not affect the other. Now, they ask us, if an item has a flaw, what is the probability that at least one inspector detects it? All right. So rather than work with the at least directly, we're going to go ahead with none. So the inspector fails to detect the flaw is 0.2 because 1 minus 0.8 means that there's a 20% chance that he won't catch it, each one individually. Now, here's the way that we can handle this. We're going to simply use this 0.2, and we want, if we use the, because they're independents, and that means we're going to multiply the 0.2 3 times, because all three means that the first inspector fails to detect it, and the second inspector fails to detect it, and the third also fails to detect it. So the and means we multiply. That's what they're saying here in this third row. Because at least once is fail to detect on all three. All right? All three. So that's 0.2 times 0.2 times 0.2, which is, they show you it's 0.2 cubed. I don't know why they don't show you that what that is, but that's 0.2 times 0.2. 0.2 is 0.08. All right. Let's see if I can make this a little bit better to show you what's happening. Oftentimes in textbooks, when you're talking about, higher level math, they assume that you know all these little things, but nobody ever remembers all that. I thought I could fix it for you so you could see what's happening. But there's not enough lines here. They got too much gobbledygook in here. Because 0.32, I tried to write that that was equal to 0.08, but 0.2 times 0.2 times 0.2 is 0.008, and if you multiply it, hit it, multiply 3 times. So 1 minus 0.008 is 0.992. So the probability of at least one inspector detects a flaw is actually pretty high now, because even though each one lower is only 80% effective together, individually, together, they're higher, 0.992, or so 99%. All right, so did anybody else show up?